P-N junction. As it has two layers with two terminals, you are naming it as diode. So this is P-N junction, where you join a P-type material which consists of holes as majority carriers to an N-type material which consists as electrons as majority carriers. Now let us join these two types of materials. One is P-type with holes as indicated blue in color that represent holes in the P-type material. Similarly, electrons which are represented as black dots in the N-type material. So this is P-type layer and N-type layer. Now for a P-N junction, for the physical structure, you have to join these two layers. But you still say that this crystal structure is electrically neutral. So this is how a P-N junction looks alike. So now as you have joined this N-type layer to this P-type layer, what happens? The holes are positively charged particles, the electrons are negatively charged particles. They will try to migrate from their place, and as they are attracted by their oppositively charged particles. So these electrons which are nearer to the junction, if you clearly observe, the electron, the topmost electron nearer to the junction has moved into the P-type layer. Now it has combined with the hole. So this hole, as it has combined with the electron, as the positive charge is recombined with the electron, they disappear in the form of heat. So the both electron and holes will be filled by each other. Electron will move into this P-type region, they recombine, they fill that whole place. Similarly, hole will move into the N-type region, they recombine and they disappear. Similarly, all the charge carriers nearer to this junction, holes from P, electrons from N, migrate to oppositively charged regions and they disappear. Now when you see this picture, completely the charges which are nearer to the junction are disappeared in the form of heat. So that recombination is, the energy is disappeared in the form of heat. That is what you feel when in the manufacturing process, when a P-type and N-type layer has been joined. So this depends again on the type of material what you have used. If you have used gallium arsenide, then the gallium arsenide material will generate the heat in the form of heat, like LEDs. But here, as you have taken a P-type material and a simple N-type material, this recombination of electrons and holes is seen in the form of heat. So this region now is completely devoid of charge carriers or depleted of charge carriers, deleted all the charge carriers, mobile charge carriers in that region nearer to the junction. So you name this junction as depletion region, which is called as a space charge region, where there is no mobile charge carriers. It is creating a field with negative and positive charge due to the donor ions in the N-type material, which are positively charged but they are immobile. Negatively charged acceptor ions in the P-type region, which are immobile. So these two charges develop a negative and positive charge nearer to the junction. As you see in the picture, see here now. The depletion region, at the P-type region, a negative charge is developed. At the N-type region, a positive charge is developed. So overall, at the depletion region, you see a positive and negative charge which is occupying, similar to a parallel plate capacitor, where the depletion layer ends will act like the plates of a capacitor and the region in between acts like the field where you carry that barrier potential. What is this potential? So this potential doesn't allow further diffusion of charge carriers. So the electrons cannot move into P-type region, the holes cannot move into N-type region. Because of that, you see this particular physical structure has reached to its equilibrium condition. So at equilibrium, no further diffusion is possible, no further conduction is possible. Electrons cannot move into P-type, holes cannot move into N-type region. So because of this, there is no movement of charge carriers, no conduction of charge carriers. You see this as no bias condition, open circuited condition, or it is at the diode is at equilibrium condition. So as you have not applied any external voltage, you name it as no bias. As it is open circuited with no external voltage, the terminals are open, you name it as open circuited P-N junction. Now, as it is a barrier, which doesn't allow any voltage, that barrier potential which is formed at the junction at the depletion layer, you have the value of 0.6 volts. So for this electrons and holes to overcome this barrier, you need, that means the electrons and holes need an energy of again 0.6 volts so that it can overcome that barrier potential. Similar to a person who want to climb a hill needs some energy. So if you want the hill to be climbed by that person, then definitely that much of energy should be needed by that person. So you'll be taking some food to get that energy. So let us take, if it is 1 apple, 2 apples, 3 apples, 4 apples, how much of energy is needed by that person to climb that hill. Similarly here also, the electrons and holes which are in N-type and P-type, they see a barrier potential in front of them. So that barrier, which is like a hill, if they want to overcome that barrier potential, they need some energy. What is the energy? We will take some food as an energy. What is the energy which should be acquired by that positively charged particles and negatively charged particles? You need to apply some external voltage. So that external voltage when you apply, then you call it as biasing. So let us first bias the PN junction. The first method of biasing is forward biasing. So in this forward biasing, you will be connecting a positive voltage to the P-type material, a negative voltage to the N-type material. What happens if you apply a positive voltage to the P-type material? P-type material consists of holes as majority carriers, which are also positively charged particles. Now, when you apply a positive voltage, because of that positive charge, the holes are repelled towards the junction. Similarly, a negative charge is applied to the electrons. So because of that, the negative charge also repels the electrons towards the depletion layer. Both the holes and electrons are repelled towards the depletion region, towards the junction of PN layers. So slowly the electrons and holes are moving towards the depletion layer. But you have a barrier at this place. The electrons and holes have to overcome that barrier. How much is the barrier? It is 0.6 volts. How much is the voltage you are giving externally? It is 0.1 volt. Is that sufficient for the electrons to move into the opposite layer? No, because the barrier potential is very much higher than the external energy what you have applied. Similarly, a person needs that much of energy so that he can or she can climb the hill. So you need more and more energy so that you can reach the maximum point. Similarly here also, the electrons and holes should be supplied an external source where that electrons and holes can gain an energy where it can overcome the barrier potential. So here also when you are applying 0.1, 0.2, 0.3 volts, that voltage is not sufficient to overcome that barrier potential. If you apply 0.6 volts, then the electrons and holes gain an energy which can overcome the potential which is formed at the junction. Because of that, what you can see here, the depletion layer has decreased while the electrons and holes have moved nearer to the junction, decreasing the barrier potential. Because it is able to overcome that potential, it is able to move into the further region of the depletion layer. Further you increase the voltage. The depletion layer further decreased. Still you increase the voltage. Completely the depletion layer has become 0. That means the width of the depletion layer is 0. The barrier potential is overcome by the electrons and holes. Now, if you give further voltage, completely the depletion layer is 0 and continuously you can see the flow of electrons and holes from P to N and N to P. You can see in the picture the holes are moving from positive charge towards the N-type layer and the electrons are moving towards the P-type layer. So this continues until you supply the external voltage. The voltage what you have given, you term it as forward bias voltage, and the movement of charge carriers, what you see here, you term it as current. Flow of electrons, you term it as current. Flow of holes, you call it as conventional current. Opposite to the flow of current is your conventional current. So here you see current through the device, you term it as forward current. So as you go on increasing the external voltage, you see further increase in the current. But where you see the start of conduction in this particular device, where the current flows through the device, you mark that starting place as cutting voltage. That particular voltage where diode starts conducting, you term it as cut-in voltage. That particular voltage for PN junction diode is 0.6 volts. It varies again with the type of material what you have used. For a germanium it can be 0.3 volts, but for silicon it is 0.6 volts. So here this conduction continues until you are applying an external energy. But for the voltages below 0.6 volts, you will not see any conduction through the device as you have depletion layer. Depletion layer width becomes 0 at a voltage of 0.6, where the barrier potential is overcome by holes and electrons. So this is called as cut-in voltage. Similarly, for a forward biased junction, when you apply this particular voltage, the continuous flow of current is seen in the picture as you are seeing now. So this is termed as forward biased PN junction, represented with a symbol like this. So this symbol indicates a P layer which is represented by a triangle and an N layer represented with a vertical line. We will represent same on the physical structure. See here. Now the P layer is your triangle structure and N layer is a vertical line. This is the diode symbol, or you call it as a circuit symbol, where wherever you want to incorporate the physical structure of the diode, you will use this circuit symbol. So this arrow mark shows the current direction, where from positive to negative, from P-type layer to N-type layer. Why? Because in semiconductors, you are only concerned about the flow of holes, not the flow of electrons. You will definitely have the flow of electrons, but the current direction is always indicated by the flow of holes, which is called conventional current. And in the forward biased diode, it is forward current. You will be supplying, practically speaking, if the forward bias voltage is in volts, the current what you see in a forward bias diode is in milliamps. So if you see the characteristic of the PN junction, characteristic which is called VI characteristic, is a plot between the voltage and current. Voltage in the x-axis, current in the y-axis. So if you see the plot, with the application of the voltage, you will not see current through the device until it has reached 0.6 volts. What is that 0.6 volts? It is a cut-in voltage. What is cut-in voltage? The voltage at which diode starts conducting. The voltage at which current can flow through the device. So that you call it as cut-in voltage. So until cut-in voltage, there is no current through the device. But as it reaches 0.6 volts, as voltage increases, current also increases. So this shows the forward characteristics of PN diode. Similarly, let us go with the second type of bias. So initially what you have done? Forward bias. What is forward biasing? Applying a positive voltage to P-type material, applying a negative voltage to N-type material, which forward biases the diode. Now, what you will do? You will reverse that, vice versa, where you will be applying negative to P-type and positive to N-type. So this makes to reverse bias the PN junction like this. So you are applying a negative voltage to the P-type material, a positive voltage to the N-type material. So what happens now? Negative to P. What P consists of? P consists of holes. What are holes? Positively charged particles. These holes are definitely attracted by the negative charge what you have applied. So these holes are attracted and they move away from the junction. They are moving away from the junction. Similarly, the positive charge attracts the electrons and makes them to move away from the junction. So both the electrons and holes are moving away from the junction, which are making the charge carriers moving away from the junction part, moving away from the depletion layer, so that you can see a increase in the depletion layer width. So you can see it here where the depletion layer width is increasing. As charge carriers are moving away, still the depletion layer has increased. The width of the depletion layer goes on increasing. This increases the depletion layer. Barrier potential also increases. When the barrier potential was 0.6 volts, the current was not there in the PN junction. Now what is happening? You are further increasing the depletion layer width. So the barrier potential also increases. So there will be no conduction through the device. So your charge carriers are moving away from the junction. As you are giving more and more voltage, the width of the depletion layer is further increased. no conduction between p-type layer and n-type layer. So because of this, in the reverse bias diode, you doesn't see any conduction, no flow of charge carriers. Why? The positively charged particles are attracted by the negative charge. Negatively charged particles, electrons, are attracted by the positive charge. They are moving away from the junction, increasing the depletion layer. So this depletion layer is devoid of charge carriers. There will be no movement of charge carriers. So the current is zero, ideally speaking. But practically what we have seen, in the p-type, there may be few minority carriers where you can have electrons in p-type, you can have holes in n-type. So those minority carriers will conduct, where the reverse bias for PN diode will act like forward bias for minority carriers. So a reverse bias to PN junction is like a forward bias to minority carriers, which may lead to a small amount of leakage current. Practically, you will see the leakage current, but ideally speaking, you will not have any current through the device in reverse bias mode, where the reverse current is zero. But ideally it should be zero, but you still see a current, so you name it as leakage current. So you see when it is reverse biased, so you call it as reverse leakage current. So you can observe this leakage current in reverse biased diode. So if you see the characteristic also, you can observe here the line which is marked in red color. So it is showing that this current is very low, which is in microamps, where the current is almost nearer to zero, which is measured in microamps. But in forward bias, it is in milliamps, where you will see large current after the cut-in voltage. With the increase of voltage, you can see a drastic increase in your forward current too. So if you see the VI characteristic of the PN junction, then till V gamma, which is the cut-in voltage, the diode will be in the off state, where the current will not flow through the device at 0.6 volts, where you term it as cut-in voltage. The diode starts conducting. So at this 0.6 volts, where the diode starts conducting, that particular forward bias voltage, you have named it as cut-in voltage. Similarly, in the reverse bias mode, the current ideally is zero, but still you see some minority current that due to minority charge carriers, which is termed as reverse leakage current. So this is about the biasing, forward and reverse biasing of a diode, how the current flows through, what happens to the depletion layer, whether conduction is there, whether it is due to minority carriers or whether it is due to majority carriers. So if you see a diode in forward bias mode and reverse bias mode, you can use the diode as for a simple application where it can be taken as a switch, something like this. If a diode is forward biased, then current flows through the device, similar to a closed switch, or you can term it as an on switch. Similarly, if you go for the reverse biased diode, then whatever may be the external voltage, the current, ideally speaking, the current is not flowing through the device, or you can treat it like an open circuit or open switch, where it is working like an off switch. So this is the first and foremost application of a diode, where you can use diode as a switch. On switch in a forward bias mode and off switch in a reverse bias mode. The same operation of forward bias and reverse bias, on and off switch, can be taken for further applications of the diode. But till here, we have seen by joining a p-type material and n-type material, you will be getting a junction, which is termed as PN junction. What happens at the junction? N and p-type materials, where they have holes and electrons, they migrate from one place to another place. Diffusion will be carried out, recombination occurs, they disappear, forming a depletion layer. This creates a barrier potential, so that can be decreased by applying forward bias, where current can be seen in that forward bias. This increases, that means the reverse bias increases the depletion layer and no conduction through the device, no current seen in the device. So this is a characteristic of the device, where in the forward bias mode and reverse bias mode. And this is the main application of the diode as a switch. So in the further class, we will see how the diode as a switch can be used as a rectifier or some more applications what you have in your syllabus. So till now, what we have seen about the diode structure and its operation, characteristics and its first application as switch. We will end it here. We will see the next application in the next class.